The most common form of hydrogen is gaseous hydrogen. Let's see how it can be stored and transported. The most common way of storing and transporting hydrogen is in pressure tanks. These are classified according to the type of material and working pressure. Type 1 is completely metallic, made of steel or aluminum. It supports pressures of up to 200 bar. Type 2 is metallic, reinforced with fiber rings, reaching pressures of up to 300 bar. This continues up to Type 5, which is still in development and is entirely built from carbon fiber. Its theoretical maximum pressure is 1000 bar. A more efficient way of transporting continuous flows is the use of dedicated hydrogen pipelines. There is a very limited total length already deployed, but new pipelines are planned to link different regions. One example is H2Med, linking Portugal, Spain, and France. These hydroducts are built with seamless steel alloy tubes. An alternative is the use of fiber-reinforced polymers. The latter eliminate the risk of embrittlement and a priori are more economical. A third alternative for transporting hydrogen is the use of existing pipeline infrastructure for natural gas. This is a network with a total length that could go around the Earth 100 times and that already reaches the natural centers of energy consumption. The transformation of a natural gas pipeline into a hydroduct has certain risks to consider, however. Hydrogen molecules are smaller than methane molecules. This fact increases the risk of leakage. It's not only necessary to verify hydrogen tightness, but also to endow the pipeline with adequate leakage detection systems. The other possible risk is the embrittlement of the material by diffusion of hydrogen into steel. This embrittlement can induce early cracking in areas where the material is subjected to stress. To reconvert a natural gas pipeline, metallography, its current state, as well as operating conditions must be thoroughly reviewed. When considering existing natural gas infrastructure, two broad possibilities arise. To blend hydrogen with natural gas, regardless of whether the fuels are separated again at the end or not. In the latter case, the reconversion must include consumption points, where combustion is adapted to the mixture of gases. It has been shown that at ratios below 15% hydrogen and methane, the pipeline would not be affected by embrittlement, and relatively little adaptation is required for most combustion consumptions. This would allow for a smoother transition for hydrogen replacing methane in the long term. The other possibility is to fully dedicate the existing pipeline to hydrogen transport. If the state of the pipeline does not allow its direct use with hydrogen, there are some alternatives to protect it. Some options are to cover it with an internal polymeric coating, inject chemical inhibitors into the gas stream, or to use the main duct as a guide for a polymeric pipe, which is surrounded by an inert gas atmosphere to eliminate any risk of leakage. Underground reservoirs are another possibility for massive storage of hydrogen, as they have been for natural gas. Depleted hydrocarbon or water fields, as well as purpose-built salt caverns, are good candidates for such reservoirs. These forms of storage can still be considered under development, since interactions of the injected hydrogen with pre-existing products in the reservoir are not completely known. The greatest advancement is represented by the saline caverns. There are at least 4 of them already operating, and numerous other projects being developed. They have the advantage of presenting an excellent seal with an essentially inert material, being able to work at pressures around 200 bar. Interaction of hydrogen is much less complex, since, theoretically, it can only react with salt from the cave and with some of the residual water remaining after its construction. In some of the pilot projects, the methanization process is also being tested. CO2 is injected with the hydrogen into the reservoir. The geological thermal gradient is used to favor the reaction and produce green methane. One way to obtain greater energy density is the use of hydrogen in a liquid state. As we said, An alternative that in some cases may be more efficient is the liquefaction of hydrogen, LH2, to be transported in perfectly insulated tanks. The greatest technological challenge stems from the fact that hydrogen requires a temperature very close to absolute zero to become a liquid. Compared to other products such as carbon dioxide, methane, or oxygen, hydrogen has much higher demands. The reason for taking on this challenge, however, is that volumetric density is almost double what we get with compressed hydrogen. 1 cubic meter contains 71 kilograms of hydrogen compared to 42 kilograms of compression at 700 bar. Liquid hydrogen is commonly used as rocket fuel, so the technology for its liquefaction, storage, and transportation already exists. On a large scale, the HESC Hydrogen Energy Supply Chain project demonstrated the technical feasibility of producing, loading, transporting, unloading, and consuming LH2, covering a distance of 8,000 kilometers between Australia and Japan. As far as ground transportation, numerous projects use isolated tank trucks to carry out distribution between production and consumption centers. Another way to store and transport hydrogen is to bind it to a stable chemical compound and, at the other end, re-extract the hydrogen. That's the concept of using carriers. One of the hydrogen carriers that attracts the most attention for different reasons is ammonia. It's a simple molecule made up of 1 atom of nitrogen and 3 of hydrogen. Under normal conditions, it is a colorless gas with a very pungent odor. As far as storage and transportation go, the process is set out as follows. Green hydrogen is produced by electrolysis. Nitrogen is extracted by distillation from the air and, by means of a process known as Haber-Bosch, ammonia is synthesized from its components. The ammonia is transported and, at the other end, the hydrogen is extracted by decomposition or, alternatively, the ammonia is used directly as fuel or raw material. Compared to the previous methods, ammonia has the great advantage of having a higher energy density, 121 kilograms of hydrogen per cubic meter, as opposed to 71 for liquid hydrogen, and it does not require extreme conditions such as 700 bar of pressure or minus 253 degrees of temperature. The latter allows the use of equipment designed for other products, such as this 6,000 cubic meter bilobular tank pre-designed by Arvang Engineering, that is used both for LPG and ammonia. Volumetric density and transport conditions are the advantages. So, what are the disadvantages? Well, in the first place, energy is consumed to produce ammonia at the source and later to decompose it at the destination in order to obtain hydrogen. Second, ammonia is a toxic substance, so it requires careful management. There is, however, a lot of experience transporting ammonia by land and sea, as it is a widely used chemical in the fertilizer industry. Another possibility is the use of a non-saturated organic substance with 1 or more double carbon bonds. In this example, we have toluene, C6H5CH3, which has 3 double bonds. When hydrogenated, it becomes methyl cyclohexane, a compound that has 6 additional hydrogen atoms in the molecule. These types of compounds, or pairs of them, are called LOHC, liquid organic hydrogen carriers. The process is as follows. Hydrogen is added to toluene, generating methyl cyclohexane. The latter is transported to its destination where it is stored. When needed, dehydrogenation is performed, extracting the 6 hydrogen atoms and regenerating toluene. The toluene is then transported back to the starting point where the process is repeated cyclically. As for its volumetric density, it is worse than LH2 and much worse than ammonia. Another drawback is the need for a fully loaded return trip. So, why would we use this type of solution? Because these compounds are almost not flammable and are not explosive. They are liquid and stable at ambient temperature and pressure. They can be kept for months without volatilizing or losing properties. Risks are lower than when dealing with traditional fuel and much lower than ammonia. They are commercial products reusable for hundreds of cycles. And finally, because the standard existing liquid transportation and storage infrastructure can be used safely.